Hello, everyone. Yeah, this is Maosong from Twitter. So today I will talk about Twitter Heron in practice. This is the talk outline. First, I will give some overview on Heron, and then later I will talk about the design goal of Heron. It is to be a MICROSTREAM engine. And then I will talk about some stragglers we met in Twitter. And then some Heron resource consumption usage, and finally we have some conclusion and QA. First, why we need real-time processing? Why? Because on the one hand, Twitter is real-time. We have a lot of real-time things to do on Twitter. For example, real-time chats, real-time conversation, real-time recommendation, real-time search, and there are more. The traffic on Twitter is very huge, and how to analyze billions of events in real time is really a huge challenge. For example, one big source of Twitter, we need to handle millions of events in a second. You know, distributed system is really hard to make the developers easy. We could not expect them to build the distributed system to handle huge traffic from scratch. So we built Heron. Here is just some terminology of Heron, and then I will describe deeper what they are. First, topology. It is a directed acyclic graph. So a text represents some computations, and edges being some stream of data tuples. And we have spouts to specify where you read the source from, what data you want to consume. For example, you can consume data from Kafka, Castro, MySQL, or something else. And both represent some core logics. The user, that's you. Developers want to process. You can process incoming tuples, do whatever you want, and you can emit any new tuples to next stage stream or processing logic if you want. Some examples are filtering, aggregation, job, and arbitrary computations. This is a concrete examples. For example, we have spouts, we have bold, yes. Spout 1, let me example, it can read from Kafka or HDFS. The beauty of this is you don't need to care how the data can transport it from one place to another. You just need to specify the logic. For example, in Spout 1, you just need to specify, okay, I want to read from Kafka. That's all. And for the bold 1, okay, maybe I want to do some basic counting or filtering. That's all. You just need to take care of what happens when one event or one data comes and what to do with it. You may just consume it, or you may produce new tuples. So this is the beauty of this kind of real-time processing framework or systems. First, you could focus on your core logic. No need to care any kind of distributed systems. For example, which host to run your jobs, what happened when the network has some outages. You don't need to care about that. So first, you just need to focus on your core logic. And secondly, it has very good horizontal scalabilities. For example, in the bold 1, we are doing some counting or some filtering. We figure out that, okay, we just found out, okay, the number of instance parallelisms may be not enough. You don't need to kind of reschedule or rewrite your job. You just need to change your config from the parallelisms. For example, earlier, we may just specify 10. Not enough, too small. Let's specify 20, 100, just by changing a config. Focus only on the core logic and achieve very good horizontal scalability. Also, it provides very good fault tolerance. You can consider your programs is kind of something, it will never crash. So to write or to develop a topology or jobs or programs handling huge traffic in distributed systems, with Heron, you can just as simple as developing a single thread programs, never crashing. These are some other benefits of Heron. For example, performance predictabilities. For example, improved developer productivities because just focus on their core logics. And also, it's easier to management because the developer no need to care about the cluster or anything else. Here are some workflow architecture of Heron. People or developer, they just submit topology to a scheduler, and we will take care of all those maintenance or submissions. So it completely releases developers from the whole maintenance. Here are some topology architecture. I will not go deep inside what different components are, because that too maybe will be another 1 hour talk. Here, I just want to mention that to make the whole thing work is pretty hard. So if you want to build a concurrent system handling huge traffic, you need to build a lot of things, very difficult. And Heron helps you with that. That's the reason we need this kind of real-time computing framework. For example, only the I1, I2 Heron instance, they are doing the real core logic, and the rest are some daemon process for the whole concurrent processing. Here's another graph. Some topology execution, some data flow, how they transport it from one place to another places, and some bottleneck we need to handle, or some fault tolerant issues. Those are some sample topologies running currently inside Twitter. As you think, from the left most, there are some simple topology, maybe just doing some basic counting, to some very complex topology, doing some very complex machine learning in real time. This is some current stage of Heron at Twitter. So Heron has been in production for 2 years. Earlier, Twitter also open sourced Storm, but later we consider Storm may no longer fit our scenario, so we replaced with Heron fully for 2 years. And Heron needs to handle large amount of data produced every day and large cluster. For example, as I mentioned earlier, one big source, just one. We have a lot of source. One big source may need to produce millions of events in a second, and we still have a lot of other sources, and we have hundreds of production topologies deployed running in real time, right here, right now. So we have several billion messages every day. Here are some use cases of Heron inside Twitter. Heron is used for some real-time ETL, some real-time BI, for some product safety, for example, some anti-spam, and some real-time trends, real-time machine learning, real-time median, and some real-time ops, for example, some real-time monitoring events. And here I want to talk about something about the design goal of Heron. That's the componentizing Heron. We want to make Heron as a MICROSTREAM engine. What does it mean? We want to make Heron into a bunch of small subsystems, and providing some API, some time safety interface for them. What that means, in fact, you don't need to take the whole Heron for your scenarios. You can just take some. And every small subsistence we determine the semantics, the features. So as long as some part of them can meet your scenarios, you can just take them. You don't need to deploy all. You can reduce the cost, yes? And also, if you want, you can implement your own components very easily and plug in with Heron very easily, because we have type-safe interface and SPI and have different components. Here are some examples. For example, here we have instance. Currently it is in Java, but maybe you want a C++ instance, Python instance. You can implement it with the predefined interfaces simply. For example, you may want to just use the feature of stream managers. Then you can just use stream manager. You can get rid of the rest components. So this is some samples. For example, you can plug and play with components. You can support multi-languages with instance. And then you can implement your own components supporting other semantics. For example, best efforts semantics, or exactly once or at least once per section semantics if you want. Very easily. And also it's very easy for development because we have time-defined SPI, and we have little dependencies between different components, so you can develop on one hand easily without taking care of the rest. Here are some different components of Heron right now. For example, for local, we have local scheduler, local uploader. This is to deploy the whole Heron cluster on your laptop. It is full feature. It's most likely used by the Heron developers. So you can verify your changes easily on your local laptop with the full features. It is not simulators. And also for development, for production, or for real staging, we have this distributed mode. We use Mesos or Aurora scheduler. We have Roomkeeper, State Manager. We have different uploaders. So we componentizing the whole Heron. You can plug with different components with different semantics easily if you want. And here, let's talk about some struggles we met and back pressures. So struggles are known of in a multi-tenant distributed systems. And it can be caused by some things. For example, this is top 3 possibilities. First, bad host. Bad host may not mean the host is bad. It's likely the host just talking with a slow external service. We also consider that is a bad host. And also, we may have some execution skill. And also, it's possible we have some inadequate provisioning. And how to handle these cases? We have some ways. First, we can drop data. That's the simplest way, yes? And also, we can slow down the senders. Ask them to, okay, we are in some troubles, please slow down. We don't want to drop data. And also, we can detect strugglers and reschedule them to some other good hosts. We tried with drop data strategies, and they have some drawbacks. Kind of first, it is pretty unpredictable. You don't know when the data drops, how much the data drops. Also, it affects the accuracies. Also, it has very poor visibilities because due to the unpredictabilities. And also, we have the strategy that slows down the standards, the back pressures. It provides some very good predictabilities because we have metrics. We know which component, which instance is causing these back pressures and for how long it caused. And it can process data at maximal rate. That's as slow as the slowest one. And it can reduce the recovery times. And it's able to handle some temporary spikes. Due to Twitter, we have some temporary spikes, some temporary huge traffics due to some instance. And here are some Twitter back pressure in practice. As you saw, sometimes you may have only one container causing the back pressures. And we can read from the source much slower than the producer side. And this is some in practice. In most scenarios, the back pressure is able to recover without any manual interventions. But sometimes we met some sustained back pressure. Here are some reasons. On the one hand, we may meet some irrecoverable GC cycles, and sometimes because the host is really bad and faulty, there's no way for the host to recover to some normal stage. We have to do some rescheduling for that particular containers. And also sometimes users prefer dropping off data because they care about the latest data, as we talk about that. They may not want to ask the sender to slow down the data. So they may have sometimes they need to manually restore the container, the bad instance. Here I want to share some Heron resource usage. We did some experiments, and here is some sample jobs. If you read data around 60 to 100 million per minute and do some filtering and do some flat map, and we attach the traffic size and do some aggregation, and eventually we write the output to the Redis 25 to 42 million key value pairs per minute. And here are the resource consumption in a table. As you see, Heron in fact is very efficient. And let's have a deeper look deeper look in the resource consumption. We spend 84% of time in a spout because it includes with data, filtering, and flat map. And we spend nearly 9% of the resources on bulk instance. That's most likely for aggregation and output. And around 7% of the resource are used by Heron. So that means the overhead may be just around 7%. It's pretty small. So most of the time or resource are spent on the user core logics. And this is some other charts. So this is another Heron experiment because earlier we open source Storm and we rely heavily on Storm and we replace Storm with Heron. And this is a job we did. And this is the comparison between Heron and Storm. As you can see, we achieve huge improvement and we reduce a lot of resource consumption after we migrated to Heron. And yeah, this is, if you guys, because the talk is short, we have just 20 minutes, if you guys are curious to learn more, this is some paper we published, and also I want to thank everyone on this list, because without them, there's no way to have such powerful real-time streaming computing framework Heron. And also, Heron is fully open sourced, and here are the GitHub link to Heron and our official website. You may also follow us on Twitter. Finally, I want to talk about something Heron on GitHub. Currently, we develop Heron in GitHub, and we use a lot of GitHub features. For example, the issue tracing. For example, the code review, the pull request, the release process, and a lot of this version controlling, and we have very good and awesome experience. So this is all of my talk, and thank you for listening. And any questions?